The universe, as we observe it tonight from our small world, stretches across billions of light-years in all directions, filled with galaxies that shimmer like distant campfires against the void. If you're watching this on a small screen, consider switching to full-screen mode and subscribing to stay with us through this journey. What the James Webb Space Telescope has recently captured in the deep cosmic darkness represents more than another beautiful image from space. It represents a fundamental challenge to our understanding of reality itself, a challenge that strikes at the very heart of Einstein's cosmological vision and the framework upon which modern physics has been constructed for more than a century. The story begins not with Webb, but with light itself, with the ancient photons that have traveled across the cosmos for so long that the stars which birthed them have long since died. When Webb's golden mirrors first unfurled in the coldness of space, positioned at the second Lagrange point some 1.5 million kilometers from Earth, the telescope began collecting light that had journeyed through time, light that carried with it information about epochs so distant that the universe bore little resemblance to the structured cosmos we inhabit today. These photons, stretched by the expansion of space itself, shifted into the infrared spectrum, became invisible to human eyes but perfectly visible to Webb's sophisticated instruments designed with exquisite precision to peer back toward the cosmic dawn. What Webb has discovered in these primordial depths troubles the mathematical elegance of Einstein's field equations in ways that astronomers had not fully anticipated. The observations reveal galaxies that should not exist, not according to our current timeline of cosmic evolution, not according to the lambda CDM model that has governed cosmological thinking for decades. These are not merely unexpected galaxies. They are massive, structured, mature systems appearing in the cosmic record at times when the universe itself was supposedly too young to have assembled such complexity. The implications ripple outward from these observations like gravitational waves through space-time, disturbing every assumption we have made about the initial conditions of the cosmos, the nature of dark matter, the behavior of dark energy, and the fundamental validity of general relativity itself at cosmological scales. Einstein's cosmological constant, the term he famously added to his field equations and later called his greatest blunder, has returned to haunt theoretical physics with renewed intensity in light of Webb's findings. When Einstein first developed his general theory of relativity in 1915, he faced a conceptual dilemma that arose from the mathematics itself. His equations predicted a dynamic universe, one that would either expand or contract under the influence of gravity, yet the astronomical observations of his era suggested a static cosmos, eternal and unchanging. To force his equations to describe a static universe, Einstein introduced the cosmological constant, represented by the Greek letter lambda, a term that acted as a kind of repulsive force counterbalancing gravitational attraction on the largest scales. This mathematical addition was not motivated by observation, but by philosophical preference, by the deeply held belief that the universe must be fundamentally stable and unchanging across time. Then came Edwin Hubble's observations in 1929, measurements of galactic redshifts that revealed the universe was not static at all, but expanding, with galaxies rushing away from one another at velocities proportional to their distances. The cosmological constant seemed unnecessary, an artificial construct imposed on equations that had been trying to tell Einstein the truth all along. For decades afterward, the cosmological constant was set to 0 in most cosmological models, treated as Einstein's mistake, a cautionary tale about allowing philosophical prejudice to override mathematical insight. The universe, it appeared, was simply expanding under its own momentum from some initial dense state, gradually slowing under the influence of gravity, destined perhaps to eventually halt and recollapse or to expand forever at an ever-decreasing rate. But observations made at the turn of the millennium, particularly studies of distant Type 1 supernovae conducted by 2 independent research teams, revealed something unexpected and profoundly strange. The expansion of the universe was not slowing down as gravity should dictate, it was accelerating. Galaxies were receding from one another at increasing speeds, as if some unknown force was pushing against gravity's inward pull, stretching space itself at an accelerating rate. This discovery earned its authors the Nobel Prize in Physics in 2011 and forced cosmologists to resurrect Einstein's cosmological constant, no longer as a mistake, but as a representation of something real, something physically present in the vacuum of space itself. This mysterious entity came to be called dark energy, and it now comprises approximately 68% of the total energy density of the universe according to the standard cosmological model. The lambda CDM model, named for the cosmological constant lambda and cold dark matter, became the standard framework for understanding cosmic evolution. In this model, the universe began in a state of extreme density and temperature some 13.8 billion years ago, then expanded and cooled, allowing matter to condense under gravity's influence into progressively larger structures. First subatomic particles, then atoms, then gas clouds, then stars, then galaxies, then clusters and superclusters of galaxies. The timeline of this structure formation is constrained by several factors including the rate of expansion, the density of matter, the properties of dark matter, and the influence of dark energy. Dark matter, which comprises about 27% of the universe's energy density, provides the gravitational scaffolding upon which visible matter accumulates, while dark energy drives the accelerating expansion that works against this gravitational collapse. Within this framework, there exists a clear prediction about when and how quickly large galaxies could have formed after the Big Bang. In the very early universe, matter was distributed almost uniformly with only tiny quantum fluctuations in density from point to point. These fluctuations, stretched to cosmic scales during the inflationary epoch that occurred in the first fraction of a second after the Big Bang, provided the seeds for all future structure. Over hundreds of millions of years, these slight overdensities slowly attracted more matter through gravitational attraction, growing denser and more massive, eventually collapsing to form the first stars and the first small protogalaxies. These early structures were expected to be small, irregularly shaped, and relatively simple. Building blocks that would merge over billions of years to form the grand spiral and elliptical galaxies we observe in the nearby universe today. The hierarchical model of galaxy formation, built upon these foundations, predicts a bottom-up process where small structures form first and then merge to create larger ones. Massive galaxies with well-defined structures, spiral arms, central bulges, and extensive stellar populations should take billions of years to assemble. When we observe the universe at high redshifts, looking back in time to when the cosmos was young, we should see smaller, more chaotic, less massive galaxies. The massive, mature systems should appear only at lower redshifts, corresponding to more recent cosmic epochs when there had been sufficient time for hierarchical assembly to occur. James Webb's observations of the deep universe have fundamentally challenged this expectation. Peering back to redshifts greater than 10, corresponding to times when the universe was less than 500 million years old, Webb has identified galaxies that appear far too massive, too structured, and too mature for their cosmic age. Some of these galaxies display stellar masses comparable to the Milky Way, a galaxy that has had over 13 billion years to assemble its hundreds of billions of stars. Yet these Webb galaxies achieved similar or greater masses in a fraction of that time, in an epoch when the universe itself had barely emerged from its dark age, the period before the first stars ignited and flooded space with light. The observations are not ambiguous or tentative. They come from multiple independent surveys using Webb's near-infrared camera and its spectroscopic instruments, which can measure not just the brightness and color of distant galaxies, but also their detailed spectra. the fingerprints of starlight that reveal chemical compositions, stellar ages, and dynamic properties. These spectra confirm that the galaxies in question are genuinely at the high redshifts they appear to occupy, not foreground interlopers masquerading as distant objects. They also reveal that these galaxies contain large populations of stars, that they have already undergone significant chemical enrichment from multiple generations of stellar evolution, and that they possess dynamical masses consistent with their stellar content, meaning they are not merely optical illusions created by unusual lighting conditions or gravitational lensing effects. The tension between these observations and theoretical predictions is quantified in terms of the cosmic star formation rate density at high redshifts. The lambda CDM model, constrained by observations of the cosmic microwave background radiation, the large-scale distribution of galaxies, and the primordial abundances of light elements, predicts a certain efficiency and timeline for converting primordial gas into stars. The number, density, and mass distribution of galaxies at any given redshift should reflect this star formation history. Yet Webb finds galaxies at redshifts where they should be exceedingly rare, and with masses that exceed the model predictions by factors that cannot be easily dismissed as statistical flukes or observational errors. Some researchers have calculated that the probability of finding such massive galaxies so early in cosmic history, given the standard model's parameters, is extraordinarily low enough to constitute a genuine crisis for the model. This crisis manifests not merely as a discrepancy in galaxy counts, but as a fundamental question about the accuracy of our cosmological parameters and the completeness of our physical theories. If the early universe contained more matter than we thought, or if dark matter behaved differently than the cold, collisionless particles assumed in the standard model, or if the efficiency of star formation was far higher than current models allow, then perhaps these early massive galaxies could be accommodated within an adjusted framework. Each of these possibilities, however, brings its own complications and conflicts with other well-established observations. Increasing the total matter density of the early universe would affect the expansion rate and the cosmic microwave background radiation in ways that are not observed. The Planck satellite, which mapped the microwave background with exquisite precision, provided tight constraints on cosmological parameters including the densities of baryonic matter, dark matter, and dark energy, as well as the Hubble constant and the spectral index of primordial density fluctuations. These parameters form a coherent picture that matches not only the microwave background data, but also observations of light element abundances from Big Bang nucleosynthesis, the large-scale structure of the galaxy distribution, and the acoustic oscillations imprinted in the clustering of galaxies. Adjusting these parameters to allow for more efficient early structure formation in one domain tends to break agreement in others, creating a cascade of problems rather than a solution. Alternative dark matter models offer another potential avenue for reconciliation. If dark matter is not cold and collisionless, but instead possesses different properties, perhaps being warm, interacting with radiation or baryons, or self-interacting, then its gravitational collapse behavior could differ from standard assumptions. Warm dark matter, for instance, would erase small-scale density fluctuations due to its higher velocity dispersion, potentially delaying the formation of the smallest structures, but not obviously accelerating the assembly of large galaxies. Self-interacting dark matter might alter the density profiles of dark matter halos, affecting galaxy formation efficiency, but again, the effects are not clearly in the direction needed to explain Webb's observations. Moreover, any significant departure from cold dark matter would impact the cosmic microwave background and large-scale structure in ways that would likely have been detected already by existing surveys. The possibility that star formation efficiency was dramatically higher in the early universe raises questions about the physical process that regulates star birth. Stars form when dense molecular clouds collapse under their own gravity, fragmenting into smaller clumps that eventually become hot and dense enough in their cores to ignite hydrogen fusion. This process is regulated by feedback mechanisms: stellar winds, supernova explosions, radiation pressure, and jets from accreting black holes that heat and disperse gas, preventing it from collapsing further. In the nearby universe, only a small fraction of the available gas in any given galaxy is actively forming stars at any moment, with the rest kept in reserve by these feedback processes. For early galaxies to build up such massive stellar populations so quickly, they would need to convert gas into stars at rates far exceeding those observed locally, implying that feedback mechanisms were either much weaker or ineffective in the early universe. Yet the physics of feedback should not depend strongly on cosmic epoch in ways that would dramatically enhance star formation efficiency. Supernovae release approximately the same amount of energy per event whether they occur in the early universe or today, and the coupling of that energy to surrounding gas depends on local conditions more than on cosmological parameters. If anything, the lower metallicity of gas in the early universe, gas that has not yet been enriched with heavy elements from previous stellar generations, might make star formation less efficient, not more, because metals play a crucial role in cooling gas clouds to the low temperatures necessary for fragmentation and collapse. The observed presence of significant metal enrichment in some high redshift Webb galaxies only deepens the puzzle, because it implies that not only did stars form rapidly, but entire cycles of stellar evolution, from birth through death in supernovae, occurred on extremely compressed timescales. Another dimension of the problem concerns the formation of supermassive black holes in the early universe. Webb has identified not only massive galaxies at high redshifts, but also bright quasars powered by black holes with masses millions to billions of times that of the Sun, existing when the universe was less than 1 billion years old. These black holes pose a separate but related challenge to cosmological models because their growth is limited by physical processes that should constrain how quickly they can accrete mass. A black hole grows by capturing surrounding gas and converting its gravitational potential energy into radiation, but this very radiation exerts an outward pressure that can halt further accretion, a limit known as the Eddington limit. Growing a billion solar mass black hole from a stellar mass seed in less than 1 billion years requires near continuous accretion at or above the Eddington limit, with little interruption, and requires that suitable seed black holes existed very early, perhaps formed through exotic mechanisms such as direct collapse of massive gas clouds rather than through the death of the first stars. The presence of both supermassive black holes and massive mature galaxies in the early universe suggests that the processes of structure formation and growth were far more rapid and efficient than standard models predict. This rapidity challenges not only the detailed astrophysics of star formation and black hole accretion, but also the underlying cosmological framework that determines how quickly gravitational collapse can proceed. The timeline of structure formation is intimately connected to the expansion history of the universe, which in turn is governed by the energy content and dynamics of spacetime itself, precisely the domain of Einstein's general relativity and the cosmological constant. Einstein's field equations relate the curvature of spacetime at any given point to the distribution of energy and matter at that point. The equations are elegant and compact in their mathematical form, but contain within them all the complexity of gravitational phenomena, from the bending of light around stars to the expansion of the universe as a whole. When applied to cosmology, the field equations must be coupled with assumptions about the symmetry and homogeneity of the universe on large scales, assumptions codified in the Friedmann-Lemaitre-Robertson-Walker metric, which describes a universe that is spatially homogeneous and isotropic, meaning it looks the same at every point and in every direction when averaged over sufficiently large scales. From these equations emerge the Friedmann equations, which govern the evolution of the universe's scale factor, the quantity that determines how distances between galaxies change over time. The Friedmann equations include terms for the density of matter, the density of radiation, the curvature of space, and the cosmological constant. Solving these equations with specific initial conditions and parameter values yields predictions for the expansion rate at any given time, the age of the universe, the distances to objects at various redshifts, and the timeline for structure formation. The cosmological constant, reintroduced as dark energy, acts as a negative pressure term that causes the expansion to accelerate rather than decelerate, fundamentally altering the universe's long-term fate. If Webb's observations are correct and cannot be reconciled with the standard lambda CDM parameters, then something must give. Either the observations are being misinterpreted, perhaps the masses of high redshift galaxies are being overestimated due to unusual stellar populations or dust effects, or the model parameters need significant adjustment, or the model itself is incomplete or incorrect. The first possibility is being actively investigated by observers who are refining their measurements and testing for systematic errors, but the consistency of results across multiple independent surveys and the detailed spectroscopic confirmation of redshifts and stellar properties make gross misinterpretation increasingly unlikely. Adjusting the model parameters faces the problem of consistency across multiple observational fronts. The cosmological parameters are not free variables that can be tuned arbitrarily. They are constrained by a web of interlocking observations that span the entire history of the universe. The cosmic microwave background, for instance, is extraordinarily sensitive to these parameters, and the precision of Planck's measurements leaves little room for adjustment without creating conflicts. The Hubble constant, which measures the current expansion rate, is itself the subject of ongoing tension between different measurement methods, with local measurements from supernovae and Cepheid variables yielding values that are slightly but persistently higher than the value inferred from the cosmic microwave background assuming the standard model. This Hubble tension, as it is known, may or may not be related to the Webb galaxy tension, but both point toward possible cracks in the standard cosmological framework. The more radical possibility is that general relativity itself requires modification at cosmological scales. Einstein's theory has been tested with extraordinary precision in the solar system, in binary pulsar systems, and in the strong gravitational fields near black holes, with every test confirming its predictions to remarkable accuracy. Yet its application to the universe as a whole involves enormous extrapolations in scale and in the strength of spacetime curvature. It is conceivable that new physics emerges at cosmological scales that modifies the gravitational dynamics in ways not captured by the standard field equations. Such modifications would need to be subtle enough to preserve agreement with existing tests while allowing for the more rapid structure formation implied by Webb's observations. Various modified gravity theories have been proposed over the decades, often motivated by the desire to explain dark matter or dark energy without invoking new forms of matter or energy. MOND, or Modified Newtonian Dynamics, attempts to explain galactic rotation curves without dark matter by altering the force law at low accelerations. Tensor vector scalar gravity and other extensions add new fields to the gravitational sector. F-registered trademark theories modify the Einstein-Hilbert action by making the gravitational Lagrangian a more general function of the Ricci scalar. Each of these theories faces its own challenges in matching the full range of cosmological and astrophysical observations, and none has gained the widespread acceptance that general relativity commands. The cosmological constant problem itself, why the observed value of dark energy is so vastly smaller than the value predicted by quantum field theory, remains one of the deepest unsolved problems in theoretical physics. Quantum fluctuations of fields in the vacuum should contribute to the energy density of empty space, but naive calculations yield a vacuum energy density that exceeds the observed dark energy density by some 120 orders of magnitude, a discrepancy so enormous that it suggests a fundamental gap in our understanding. Various mechanisms have been proposed to explain this discrepancy, from anthropic reasoning based on multiverse theory to dynamical adjustment mechanisms involving new scalar fields, but none has proven entirely satisfactory. Webb's discovery of early massive galaxies adds a new empirical constraint to this already complex theoretical landscape. If the universe's expansion history differs from what we have assumed, if dark energy's density or equation of state has evolved over time rather than remaining constant, then the timeline of structure formation would be affected. Quintessence models, in which dark energy is not a cosmological constant but a dynamical scalar field whose energy density changes over time, offer one framework for such evolution. If dark energy was less dominant in the early universe, allowing matter to clump more efficiently before accelerated expansion took over, then perhaps early structure formation could proceed more rapidly. However, such models face tight constraints from observations of the cosmic microwave background and the distance redshift relation measured through supernovae and other standard candles. The interplay between dark energy and dark matter in the early universe is another area of active investigation. If dark matter is not entirely cold, but has some small velocity dispersion, or if dark matter particles decay or interact in ways that become significant only under the extreme densities of the early universe, then the initial conditions for structure formation could differ from standard assumptions. Warm dark matter, for example, would suppress the formation of small-scale structures, but it is unclear how this would lead to enhanced formation of large galaxies. Decaying dark matter could inject energy into the intergalactic medium, affecting the thermal history of gas and potentially influencing star formation, though again the effects are not obviously in the direction needed to resolve the tension. The role of baryonic physics in early galaxy formation is another frontier of uncertainty. Baryons, the ordinary matter composed of protons and neutrons, behave very differently from dark matter because they interact electromagnetically, allowing them to radiate energy, cool, and collapse into dense structures. The efficiency with which baryons cool and form stars depends on the availability of coolants, primarily hydrogen molecules and metal atoms, and on the intensity of background radiation fields that can heat gas or dissociate molecules. In the early universe, the first stars, known as population 3 stars, formed from primordial gas containing only hydrogen and helium, without the metals that facilitate cooling in later generations. These first stars were likely very massive and short-lived, exploding as supernovae that enriched their surroundings with the first heavy elements. The transition from population 3 to population 2 and eventually to population 1 stars, with progressively higher metal content, is a critical phase in cosmic history. Webb's observations of metal-enriched galaxies at very high redshifts suggest that this transition occurred remarkably quickly, with multiple cycles of star formation and supernovae occurring in rapid succession. The speed of this chemical evolution depends on the initial mass function of stars, the distribution of stellar masses at birth, and on how quickly supernova eject a mix with the surrounding gas to enable the next generation of star formation. If the initial mass function was skewed toward more massive stars in the early universe, then metal enrichment could proceed more rapidly, but massive stars are also less efficient at building up stellar mass in long-lived populations because they burn out so quickly. Feedback from the first stars and black holes had profound effects on the reionization of the universe, the process by which neutral hydrogen gas was ionized by ultraviolet radiation from the first luminous sources. The epoch of reionization, spanning roughly from 400 million to 1 billion years after the Big Bang, is a period of transition from a neutral, opaque universe to an ionized, transparent one. Webb is providing new insights into this era by observing galaxies and quasars that contributed to reionization, revealing that the sources of ionizing photons were more abundant and perhaps more energetic than previously thought. The timing and topology of reionization, whether it occurred uniformly or in a patchy, inhomogeneous manner, depend on the distribution and properties of early galaxies, which Webb is now mapping in unprecedented detail. The implications of Webb's findings extend beyond galaxy formation to the fundamental constants and initial conditions of the universe. The amplitude of primordial density fluctuations, encoded in the power spectrum of the cosmic microwave background, determines how much structure existed at early times to seed galaxy formation. If this amplitude is higher than measured by Planck, then structure formation could proceed more quickly, but increasing the amplitude affects the microwave background in observable ways that have not been seen. The spectral index of the primordial power spectrum, which describes how the amplitude of fluctuations varies with scale, is another key parameter. A different spectral index could shift the balance of power between small-scale and large-scale structures, potentially affecting the formation timeline, but again, this parameter is constrained by microwave background observations. The inflationary paradigm, which posits a brief period of exponential expansion in the first fraction of a second after the Big Bang, provides a mechanism for generating the primordial density fluctuations that seed all cosmic structure. Different inflationary models predict different forms for the primordial power spectrum, different levels of non-Gaussianity in the fluctuation distribution, and different amounts of primordial gravitational waves. Webb's observations of the earliest galaxies provide a new window into the consequences of inflation, potentially constraining inflationary models in ways that complement microwave background observations. If the early universe was more structured than standard inflationary models predict, this could point toward exotic inflationary scenarios or toward pre-inflationary physics that left an imprint on the initial conditions. String theory and other approaches to quantum gravity suggest that space-time itself may have a more complex structure than described by classical general relativity, particularly at the highest energies and smallest scales relevant to the Big Bang. Extra dimensions, quantum fluctuations of space-time geometry, and the interplay between gravity and quantum field theory could all influence the initial conditions and early evolution of the universe in ways that classical cosmology does not capture. While these ideas remain highly speculative and far from observational confirmation, Webb's challenge to standard cosmology provides motivation to explore whether new physics at the Planck scale could leave observable signatures in the large-scale structure of the universe. The concept of cosmic time itself becomes subtle in the context of general relativity and cosmology. Time is not absolute, but is woven into the fabric of space-time, dilated by gravity and relative motion. In an expanding universe, there are multiple ways to define time: cosmic time as measured by observers at rest with respect to the cosmic microwave background, conformal time which simplifies the mathematics of light propagation, look-back time which measures how long ago the light we see was emitted. The timeline of structure formation is discussed in terms of cosmic time, but the observations are made in terms of redshift and look-back time. Converting between these requires a model for the expansion history, which is precisely what is in question when the standard model faces challenges from observations. A different expansion history would alter the mapping between redshift and cosmic time, potentially affecting the interpretation of when early galaxies formed. The anthropic principle, often invoked in discussions of fine-tuning in cosmology and particle physics, raises the question of whether the parameters of our universe are uniquely determined by fundamental theory or are instead drawn from a vast landscape of possibilities, with our particular values selected by the requirement that they allow for the formation of observers. If the cosmological constant, the amplitude of density fluctuations, the baryon-to-photon ratio, and other seemingly arbitrary parameters are not fixed by a single unique theory but vary across a multiverse, then the values we measure are conditioned on our existence, which requires a universe capable of forming galaxies, stars, and planets. Webb's observations, by challenging whether our measured parameters are consistent with the observed structure formation history, raise questions about the self-consistency of the anthropic framework. If the universe appears more structured at early times than the parameters allow, this could suggest either that we have mismeasured the parameters, that the standard model is incomplete, or that anthropic reasoning is missing some key ingredient. The philosophical implications of Webb's discoveries touch on the nature of scientific knowledge and the limits of empirical inquiry. Cosmology operates at the boundary of observational science, where the objects of study are unique, unrepeatable, and accessible only through indirect inference from ancient light. The universe cannot be experimented upon, only observed. The history of cosmology is filled with instances where observations forced revision of theory, the discovery of the expansion, the cosmic microwave background, dark matter, dark energy, and each revision has required both empirical courage and theoretical flexibility. Webb's challenge to the standard model may represent another such moment, where observations compel a re-examination of foundational assumptions. The process of cosmic structure formation can be studied through numerical simulations that solve the equations of gravity, hydrodynamics, and radiative transfer in an expanding universe. These simulations, running on the world's most powerful supercomputers, model the evolution of dark matter and baryons from the smooth initial conditions of the Big Bang to the complex web of galaxies and clusters observed today. The largest simulations track billions of particles representing dark matter and gas, following their gravitational interactions and modeling the physics of gas cooling, star formation, and feedback from supernovae and black holes. The outputs of these simulations can be compared directly with observations, providing a powerful test of cosmological models. Recent simulations incorporating updated physics have attempted to reproduce Webb's observations of early massive galaxies within the lambda-CDM framework by tweaking the parameters governing star formation efficiency, feedback strength, and other baryonic processes. Some of these efforts have achieved partial success, producing galaxies at high redshifts that are somewhat more massive than previous simulations predicted, though still not fully matching the most extreme objects observed by Webb. The challenge is to adjust the baryonic physics in ways that are physically motivated and consistent with observations of nearby galaxies, without resorting to ad hoc tuning designed solely to match the Webb results. If no physically plausible set of baryonic processes can reproduce the observations within the standard cosmological framework, this would constitute strong evidence that the framework itself needs revision. The role of supermassive black holes in early galaxy evolution adds another layer of complexity. Feedback from actively accreting black holes, manifest as powerful jets and winds that heat and expel gas, can suppress star formation in their host galaxies, a process known as AGN feedback. In the local universe, there is a tight correlation between the masses of supermassive black holes and the properties of their host galaxies, suggesting a co-evolutionary relationship. If supermassive black holes grew very rapidly in the early universe, as Webb's quasar observations suggest, their feedback could have profoundly affected the star formation histories of early galaxies, either suppressing it through heating or enhancing it through compression of gas clouds. Disentangling these effects requires detailed modeling of the coupling between black hole accretion and the surrounding interstellar medium, a problem that remains at the frontier of theoretical astrophysics. The observational program to further investigate these questions is intensive and ongoing. Webb is conducting deep surveys across multiple fields, observing thousands of high redshift galaxies to build statistical samples that can robustly constrain the galaxy mass function and star formation rate density as a function of cosmic time. Spectroscopic follow-up of the most interesting candidates is confirming redshifts, measuring stellar masses, determining chemical compositions, and probing the dynamics of these galaxies through emission and absorption line profiles. Complementary observations from ground-based telescopes, including the Atacama Large Millimeter Array, which observes the cold dust and gas in galaxies, and from other space observatories, are providing additional pieces of the puzzle. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will conduct wide-area surveys that complement Webb's deep-pointed observations, mapping the distribution of galaxies over larger volumes of space and providing better statistics on the rare, most massive objects. The Square Kilometer Array, a next-generation radio telescope under construction, will map the distribution of neutral hydrogen throughout cosmic history, providing an independent probe of structure formation. The Extremely Large Telescope and other ground-based optical observatories will achieve unprecedented angular resolution, allowing detailed studies of the structures and kinematics of distant galaxies. Together, these observational efforts will provide a multi-wavelength, multi-resolution picture of the high redshift universe that will either confirm or refute the tensions raised by Webb's initial findings. Theoretical work is proceeding on multiple fronts to interpret these observations and to develop new models that can accommodate them. Some researchers are exploring modifications to the initial conditions, investigating whether the primordial power spectrum could differ from the standard nearly scale-invariant form in ways that are consistent with cosmic microwave background observations but allow for enhanced early structure formation. Others are revisiting the properties of dark matter, considering models where dark matter interacts with itself or with baryons in ways that become significant only at high redshifts. Still, others are examining the expansion history, exploring models where dark energy evolves with time, or where the early universe experienced additional phases of acceleration or deceleration that are not captured in the standard model. Modified gravity theories are also receiving renewed attention in light of Webb's findings. If general relativity requires correction at cosmological scales, the corrections would need to enhance the growth rate of structure in the early universe while preserving agreement with solar system tests, binary pulsar observations, and gravitational wave detections from merging black holes and neutron stars. This is a challenging set of constraints to satisfy, but several candidate theories are under active investigation. These include theories with additional scalar fields that mediate a fifth force, theories with modifications to the Friedmann equations that affect the expansion rate, and theories that introduce new symmetries or principles that constrain the allowed forms of gravitational action. The connection between cosmology and particle physics is intimate, as the behavior of dark matter and dark energy depends on the properties of particles and fields that may not yet have been discovered in terrestrial experiments. The Large Hadron Collider and other particle accelerators have searched for dark matter particles and for signs of new physics beyond the standard model of particle physics, so far without definitive success. The absence of detection places constraints on the masses and interaction strengths of hypothetical dark matter particles, narrowing the parameter space but not eliminating the vast range of possibilities. Webb's cosmological observations provide complementary constraints from an entirely different domain, potentially ruling out models that are consistent with particle physics experiments but inconsistent with the structure formation history. The interplay between different lines of evidence is central to the scientific process of converging on truth. No single observation, however striking, is sufficient to overturn a well-established theory. What is required is a preponderance of evidence from multiple independent sources, all pointing in the same direction, accumulating to the point where the weight of anomalies becomes impossible to ignore. Webb's observations of early massive galaxies represent one such line of evidence. The Hubble tension represents another. The anomalous behavior of certain galaxy rotation curves, the unexpected smoothness of the cosmic microwave background at large angles, the observed properties of dark matter distribution in galaxy clusters, each of these represents a potential challenge to the standard model, and collectively they create a pattern that may signal the need for fundamental revision. Yet the history of science also teaches caution. Anomalies have often turned out to be observational errors, instrumental artifacts, or misinterpretations of data. The faster-than-light neutrino anomaly reported in 2011, which if true would have shattered special relativity, turned out to be due to a faulty cable connection. The BICEP-2 claim in 2014 of detecting primordial gravitational waves in the cosmic microwave background was later shown to be dominated by foreground dust emission. The periodic mass extinctions in the fossil record once attributed to a companion star to the Sun, dubbed Nemesis, have not been confirmed by subsequent studies. Science progresses through a process of conjecture and refutation, and the bar for overturning established theory is rightly set very high. In the case of Webb's findings, the observations are robust and have been confirmed by multiple independent analyses, making instrumental error or simple misinterpretation unlikely. The tension with theory is real and quantifiable. What remains uncertain is the resolution, whether it will come through refinement of theoretical models within the existing framework, through adjustment of cosmological parameters within allowed ranges, through recognition of overlooked astrophysical processes that enhance early structure formation, or through a more fundamental revision of our understanding of gravity, dark matter, or dark energy. The answer will emerge through continued observation, rigorous analysis, and creative theoretical exploration, through the collective effort of the global scientific community engaged in the grand project of understanding the universe. The cosmos, as revealed by Webb, is more complex, more dynamic, and more structured in its early epochs than anticipated. This complexity is not a failure of science, but an invitation to deepen inquiry, to question assumptions, and to remain open to the possibility that nature's workings exceed our current theoretical grasp. Einstein's general relativity remains one of the most successful and beautiful theories in the history of physics, but like Newton's theory before it, it may represent an approximation, extraordinarily accurate within its domain of applicability, but incomplete at the edges where new phenomena emerge. The cosmological constant, resurrected from Einstein's rejected idea to become a cornerstone of modern cosmology, may itself require further evolution or replacement as the dark energy problem finds its ultimate resolution. The observational challenge posed by Webb extends beyond the specific question of early galaxy masses to the broader question of whether we understand the initial conditions and evolutionary dynamics of the universe as a whole. The initial conditions are encoded in the cosmic microwave background and in the patterns of large-scale structure, but extracting precise information from these observations requires modeling that rests on assumptions about the underlying physics. If those assumptions are even slightly incorrect, the inferred initial conditions could be systematically biased, leading to predictions that fail to match later observations, such as Webb's galaxy counts. Breaking this potential circularity requires observations that probe the universe in entirely different ways, providing independent constraints that do not rely on the same set of assumptions. One such independent probe is gravitational lensing, the bending of light by the gravity of intervening matter, which provides a direct measurement of mass distribution without relying on assumptions about light-to-mass ratios or stellar populations. Webb has already used gravitational lensing to magnify distant galaxies that would otherwise be too faint to observe, revealing structures at even higher redshifts than possible with unlensed observations. The statistics of lensed galaxies, the frequency of strong lensing events, and the detailed properties of lens models provide constraints on the matter, distribution, and the expansion history that are complementary to other methods. As the sample of lensed high redshift galaxies grows, these constraints will become increasingly powerful, potentially resolving some of the current tensions. Another independent probe is the integrated Sachs-Wolf effect, a subtle signal in the cosmic microwave background caused by the gravitational potential wells of large-scale structures evolving as photons pass through them. In a universe with dark energy or a cosmological constant, the expansion accelerates. causing potential wells to decay over time and imparting a small net energy change to passing photons. The magnitude of this effect depends on the expansion history and the growth rate of structure, providing a test of dark energy models and modified gravity theories. Cross-correlating microwave background maps with large-scale structure surveys has detected the integrated Sachs-Wolf effect, but with relatively low signal-to-noise. Future surveys with larger area and greater depth will improve this measurement, offering another avenue to test cosmological models. The cosmic neutrino background, a relic of the early universe analogous to the cosmic microwave background but composed of neutrinos rather than photons, has not yet been directly detected but is predicted to exist with high confidence. Neutrinos, being extremely weakly interacting, have free-streamed since about 1 second after the Big Bang, carrying information about that early epoch. The properties of the neutrino background, particularly the total energy density in neutrinos and the sum of neutrino masses, affect the expansion rate and the growth of structure in measurable ways. Large-scale structure surveys and cosmic microwave background observations have placed upper limits on the sum of neutrino masses, and these limits are being tightened by Webb's observations of high redshift structure, which are sensitive to how neutrino mass suppresses the growth of small-scale fluctuations. The baryon acoustic oscillation feature in the galaxy distribution, a characteristic scale imprinted by sound waves in the early universe, serves as a standard ruler for measuring the expansion history. By observing how the apparent size of this feature changes with redshift, astronomers can map the distance-redshift relation and constrain the expansion rate at different epochs. Surveys such as the Dark Energy Spectroscopic Instrument and the future Euclid mission are measuring baryon acoustic oscillations with percent-level precision across a wide range of redshifts, providing tight constraints on the expansion history and dark energy properties. Any tension between the expansion history inferred from these measurements and the history required to explain Webb's early galaxies would indicate a fundamental inconsistency in the cosmological model. The thermal history of the intergalactic medium, traced through absorption lines in the spectra of distant quasars, provides yet another window into cosmic evolution. The temperature, density, and ionization state of intergalactic gas are affected by the radiation from galaxies and quasars, by structure formation shocks, and by the expansion of the universe itself. Webb's observations of early galaxies and quasars reveal the sources of ionizing radiation that shaped this thermal history, while absorption line studies map the effects of that radiation on the gas. Consistency between the observed thermal history and the predicted output of ionizing radiation from observed sources provides a test of models for reionization and early structure formation. The chemical evolution of the universe, reflected in the metallicities of stars and gas in galaxies across cosmic time, carries information about the history of star formation and supernova enrichment. Webb's spectroscopic observations of high redshift galaxies have revealed surprisingly high metallicities in some cases, indicating rapid chemical enrichment. The metal abundance patterns, including the ratios of different elements, provide clues to the types of stars that produce the metals and the timescales involved. Alpha elements such as oxygen, neon, and magnesium are produced primarily in massive stars that explode as core collapse supernovae on timescales of millions of years, while iron is produced both in core collapse supernovae and in type 1 supernovae from white dwarf explosions that occur on timescales of hundreds of millions to billions of years. The alpha-to-iron ratio in high redshift galaxies thus provides a chemical clock that constrains the duration and intensity of star formation. The morphological diversity of high redshift galaxies, from compact clumpy systems to extended rotating disks to merging pairs, reflects the different pathways by which galaxies grow. Webb's high-resolution imaging reveals structures in distant galaxies that were blurred or invisible in earlier observations. showing that some high redshift galaxies have surprisingly regular morphologies with disk-like structures and even hints of spiral arms, features that were thought to develop only in more mature galaxies. Other high redshift galaxies are highly irregular, with multiple bright clumps that may represent sites of intense star formation or small merging protogalaxies. Understanding what fraction of early massive galaxies formed through smooth accretion versus through violent mergers has implications for the hierarchical assembly model and for the role of cold streams of gas in fueling early galaxy growth. Cold streams or cold flows are a predicted feature of early galaxy formation, in which gas flows along cosmic filaments directly into dark matter halos without being shock-heated to the virial temperature. In lower mass halos and at high redshifts when the universe is denser, the virial temperature can be low enough that gas cools rapidly, maintaining relatively low temperatures as it flows inward. This cold gas can reach the central galaxy without losing its angular momentum, forming a rotating disk and fueling rapid star formation. The existence and importance of cold streams remain somewhat uncertain because they are difficult to observe directly, but they are a generic prediction of simulations and could help explain how early galaxies built up their stellar masses so quickly. The role of environment in early galaxy formation is another area of investigation. In the local universe, galaxies in dense clusters differ systematically from galaxies in the field. Cluster galaxies are more likely to be elliptical and red, with little ongoing star formation, while field galaxies include many spiral systems with active star formation. This environmental dependence is thought to arise from processes such as ram pressure stripping of gas as galaxies move through hot intracluster medium, tidal interactions in the dense cluster environment, and galaxy harassment from repeated high-speed encounters. At high redshifts, clusters are still assembling, and the differences between cluster and field environments may be less pronounced. Webb is beginning to identify the progenitors of massive clusters in the early universe, revealing protoclusters that are regions of high galaxy density but have not yet collapsed into relaxed systems. The properties of galaxies in these protoclusters compared to those in the field will illuminate how environment influences early galaxy evolution. The star formation history of the universe as a whole, the total rate at which gas is being converted into stars as a function of cosmic time, is a fundamental observable that integrates over all galaxies and provides a direct measure of the efficiency of cosmic structure formation. Observations of star-forming galaxies across cosmic history, from ultraviolet light in local galaxies to far-infrared emission from dust-obscured starbursts at high redshifts, have mapped out a cosmic star formation history that rises from the early universe, peaks around redshift 2 to 3 corresponding to about 10 billion years ago, and then declines to the present day. This rise and fall reflect the competing effects of increasing availability of dense gas for star formation in the early universe and the eventual exhaustion and heating of gas by feedback processes, combined with the increasing influence of dark energy that slows the assembly of new structures. Webb's observations of the earliest star-forming galaxies are filling in the low redshift end of this history. But if those galaxies are more numerous and more massive than expected, they imply a higher integrated star formation rate in the early universe, potentially conflicting with the total stellar mass density observed in later epochs unless stars are destroyed or hidden in some way. The fate of stars once they form is relatively well understood. Massive stars explode as supernovae after a few million years, returning much of their mass to the interstellar medium, while low-mass stars like the Sun burn for billions of years and eventually become white dwarfs. The integrated stellar mass in the universe should thus reflect the total star formation over all time, corrected for the mass returned to the interstellar medium by stellar evolution. If the early universe had much more star formation than the standard model predicts, this should show up as a higher total stellar mass density in later epochs, which can be measured by surveying galaxies and adding up their stellar masses. There is no strong evidence for an excess of stellar mass in the present-day universe, which places a constraint on how much additional early star formation could have occurred. This argument relies on the assumption that stellar mass is not hidden in forms that are difficult to observe, such as in the diffuse intracluster light, in very low surface brightness galaxies, or in hypothetical populations of dark or low-mass stellar remnants. The possibility that early galaxies are more massive than they appear due to unusual stellar populations is being investigated through detailed spectroscopic analysis. Stars of different masses and ages have different spectra, and the integrated spectrum of a galaxy reflects its star formation history and chemical composition. If early galaxies contain a much higher proportion of massive stars than local galaxies, their light output per unit stellar mass would be higher, making them appear more luminous for a given stellar mass. This would mean that stellar mass estimates based on standard assumptions about the stellar mass-to-light ratio could be overestimated. However, there are constraints on the allowable range of stellar mass-to-light ratios from stellar physics and from observations of nearby galaxies, and extreme departures from standard assumptions would require unusual and somewhat contrived initial mass functions. Moreover, the presence of spectral features from lower-mass stars in high-redshift galaxies indicates that the stellar populations are not exclusively composed of the most massive stars. Dust attenuation complicates the interpretation of galaxy luminosities at all wavelengths. Dust grains, composed of silicates, carbonaceous material, and other solids, absorb ultraviolet and optical light from stars and re-radiate it in the infrared. A dusty galaxy can appear faint in the optical but bright in the infrared, and the total energy output integrated across all wavelengths may be much higher than the optical luminosity alone suggests. Webb's infrared sensitivity allows it to pierce through dust and observe the stellar light directly, but even Webb's observations can be affected by dust if the dust column density is high enough. Measuring the dust content and correcting for its effects requires observations at multiple wavelengths, including the far infrared where the dust emission peaks, which requires complementary facilities such as ALMA. The presence of significant dust in high redshift galaxies is itself interesting because dust is made from heavy elements produced by stars, so a dusty galaxy must have already undergone substantial stellar evolution. The relationship between galaxies and their dark matter halos is a key aspect of galaxy formation theory. Simulations predict that galaxies form at the centers of dark matter halos, with the galaxy's mass being some fraction of the halo's mass. This fraction, known as the stellar-to-halo mass ratio, depends on complex baryonic physics including gas cooling, star formation, and feedback, and it varies with halo mass. For intermediate mass halos around the mass of the Milky Way's halo, the stellar-to-halo mass ratio peaks at around 1 to 2%, meaning only a small fraction of the halo's mass is converted into stars. In more massive halos, AGN feedback is thought to suppress star formation, reducing the stellar-to-halo mass ratio, while in lower mass halos, supernova feedback is more effective at ejecting gas, also reducing the ratio. If high redshift galaxies have higher stellar-to-halo mass ratios than expected, this implies that star formation was more efficient in the early universe, or that the halo masses are being underestimated. Halo masses can be estimated from galaxy dynamics through measurements of rotation velocities or velocity dispersions, from gravitational lensing effects, or from the clustering properties of galaxies. Each method has its uncertainties and systematic errors. Dynamical measurements require spatially resolved spectroscopy to map velocity fields, which is challenging for distant, faint galaxies. Gravitational lensing provides a more direct mass measurement but requires fortuitous alignments and is subject to uncertainties in the lens model. Clustering measurements rely on statistical samples of many galaxies and assume that the relationship between galaxies and halos follows predictions from simulations. Comparing mass estimates from different methods can reveal inconsistencies that might point to problems with the underlying models. The cosmic web of dark matter, the large-scale filamentary structure that permeates the universe, funnels gas towards the densest nodes where galaxy clusters form. Galaxies themselves are threaded along these filaments, marking the densest parts of the dark matter distribution. Mapping the cosmic web at high redshifts reveals the scaffolding upon which the present-day large-scale structure is built. Webb observations of the spatial distribution of high redshift galaxies are beginning to trace this web, showing that even in the early universe, galaxies are not distributed randomly but are clustered in ways that reflect the underlying dark matter distribution. The strength and scale of this clustering provide constraints on the amplitude of density fluctuations and the nature of dark matter, complementing other probes of large-scale structure. The anisotropies in the cosmic microwave background, the tiny temperature variations from point to point in the primordial radiation, encode a wealth of information about the early universe. These anisotropies arise from density fluctuations in the photon-baryon fluid at the time of recombination, when the universe became transparent and photons decoupled from matter. The pattern of anisotropies is shaped by acoustic oscillations, gravity, and the expansion history, and it is sensitive to cosmological parameters including the densities of matter, dark energy and radiation, the curvature of space, and the amplitude and spectral index of primordial fluctuations. Planck's measurements of these anisotropies have constrained the standard cosmological parameters to percent-level precision, creating a tight framework within which models of structure formation must operate. Any model that attempts to explain Webb's observations of early massive galaxies must remain consistent with the microwave background data, a constraint that severely limits the available parameter space. Primordial non-Gaussianity. Departures from the Gaussian random distribution in the initial density fluctuations would indicate new physics in the inflationary epoch or alternatives to inflation. The microwave background and large-scale structure observations have placed stringent limits on non-Gaussianity, but certain forms could still be present at levels that affect structure formation without violating current observational bounds. If the initial fluctuations have a non-Gaussian tail with more extreme values than expected from a Gaussian distribution, this could lead to the early formation of rare massive objects, potentially helping to explain Webb's findings. However, the specific form of non-Gaussianity required would need to be motivated by a theoretical framework and would likely have other observable consequences that could be tested. Cosmic strings, one-dimensional topological defects that might have formed during phase transitions in the very early universe, could seed structure formation by creating linear overdensities along which matter accumulates. If cosmic strings exist and contribute significantly to structure formation, they could alter the predicted timeline and morphology of early structures. However, cosmic microwave background observations constrain the contribution of cosmic strings to be subdominant compared to the standard adiabatic fluctuations from inflation. So, while strings could provide an additional contribution, they are unlikely to fully resolve the tension with Webb's observations on their own. Domain walls and magnetic monopoles, other types of topological defects predicted in certain theories, face even tighter constraints from observations and are not considered viable contributors to structure formation in the standard cosmological framework. More exotic ideas, such as primordial black holes as a component of dark matter, face constraints from microlensing surveys, from the cosmic microwave background, and from the mergers observed by gravitational wave detectors. If primordial black holes exist in significant numbers, they could affect the early growth of structure, but most mass ranges for primordial black holes are now ruled out or tightly constrained by observations. The multiverse hypothesis, arising from eternal inflation and string theory, posits that our observable universe is just one bubble in a vastly larger ensemble of universes with differing physical constants and laws. In this framework, the observed properties of our universe, including the cosmological parameters, are not fundamental predictions of a unique theory, but are environmentally selected from a landscape of possibilities, with the selection criterion being the existence of observers. This anthropic explanation for fine-tuning has been applied to the cosmological constant problem. The observed value of dark energy is in the range that allows for galaxy formation and thus for observers to exist. Webb's findings, if they indicate that the universe's parameters are in tension with observed structure formation, could be seen as a challenge to the anthropic argument, unless the resolution lies in recognizing that the parameter space allowing for observers is broader than previously thought, or that our estimates of the parameters are incorrect. The landscape of string theory, with its vast number of possible vacuum states corresponding to different configurations of compactified extra dimensions and different effective low-energy physics, provides a potential framework for the multiverse, but it remains highly speculative and far from making concrete testable predictions for cosmology. Some researchers hope that future observations, including those from Webb, will either provide evidence for or rule out aspects of the landscape, thereby testing the string theory paradigm indirectly. Others argue that the landscape and multiverse ideas are not truly scientific because they lack falsifiability. Any observation can in principle be accommodated by invoking an appropriate member of the ensemble. This debate touches on deep questions about the nature and goals of scientific inquiry, particularly in domains like cosmology where controlled experiments are impossible and where we are limited to observing a single universe. The role of the cosmological constant in Einstein's framework can be understood from multiple perspectives. Mathematically, it is the simplest possible additional term that can be added to the field equations while preserving general covariance. The requirement that the laws of physics take the same form in all coordinate systems. Physically, it can be interpreted as the energy density of the vacuum, a uniform energy inherent in empty space itself. Quantum field theory predicts that the vacuum should have energy due to the zero-point fluctuations of quantum fields, but as mentioned earlier, the predicted magnitude is absurdly large compared to observation. The resolution of this vacuum energy problem may require new principles or new physics that we do not yet understand, possibly related to quantum gravity. Some speculative approaches to quantum gravity, such as loop quantum gravity and causal set theory, offer different perspectives on space-time and gravity that might shed light on the cosmological constant problem and other foundational issues in cosmology. Loop quantum gravity quantizes space-time geometry itself, treating space as composed of discrete quantum loops rather than a smooth continuum, and predicts modifications to general relativity at the Planck scale. These modifications could potentially affect the very early universe, including the inflationary epoch and the initial conditions for structure formation. Causal set theory proposes that spacetime is fundamentally discrete, composed of a partially ordered set of events, and derives the smooth geometry of general relativity as a continuum approximation. This discreteness could impose a natural cutoff on vacuum energy contributions, potentially addressing the cosmological constant problem, but the theory remains in its early stages and has not yet made detailed predictions for observational cosmology. The emergent gravity paradigm, championed by some researchers, suggests that gravity is not a fundamental force but an emergent phenomenon arising from the statistical mechanics of more fundamental microscopic degrees of freedom, analogous to how thermodynamics emerges from the statistical behavior of atoms. In this view, general relativity and the cosmological constant are effective descriptions that may break down or require modification when the underlying microscopic structure becomes relevant. While intriguing, emergent gravity remains a speculative research program with many open questions and has not yet produced a complete and predictive framework that can be tested against observations like those from Webb. The observational strategy moving forward involves not only deeper and wider surveys with Webb and other facilities, but also the development of new analysis techniques that can extract more information from the data. Machine learning algorithms are increasingly being applied to identify and classify high redshift galaxies, to estimate their properties from photometry and spectroscopy, and to model complex selection effects and biases. These techniques have the potential to improve the efficiency and accuracy of surveys, enabling more robust statistical inferences about the galaxy population and its evolution. However, machine learning models must be carefully validated to ensure that they are not introducing systematic errors or biases that could affect scientific conclusions. The interdisciplinary nature of modern cosmology brings together expertise from observational astronomy, theoretical physics, computational science, statistics, and even philosophy. Addressing the questions raised by Webb's observations requires collaboration across these domains, with observers providing precise measurements, theorists developing models and predictions, simulators running large-scale computations to test those models, statisticians developing methods to quantify uncertainties and compare models, and philosophers clarifying the conceptual foundations and epistemological status of cosmological inferences. The community's collective effort, channeled through peer review, conferences, preprint servers, and collaborative projects, drives progress toward a deeper understanding. Public engagement and education play a role in this endeavor as well. The stunning images produced by Webb capture the public imagination and communicate the wonder of the cosmos, inspiring the next generation of scientists and fostering broad support for fundamental research. Explaining the scientific significance of Webb's findings, including the challenges they pose to established theory, requires clear communication that conveys both the excitement of discovery and the rigorous process of scientific inquiry. The tension between observation and theory is not a failure, but a natural and productive part of science, driving the field forward through the iterative cycle of prediction, observation, and refinement. The history of astronomy is replete with examples where unexpected observations led to profound insights. The anomalous precession of Mercury's orbit, unexplained by Newtonian gravity, was one of the key empirical facts that general relativity successfully accounted for, validating Einstein's theory. The unexpected flatness of galaxy rotation curves led to the inference of dark matter, one of the most important discoveries in 20th century cosmology. The accelerating expansion discovered through supernova observations upended the expectation that gravity should be slowing the expansion and led to the resurrection of the cosmological constant. Webb's findings have the potential to be another such pivotal moment, whether they lead to refinements within the existing framework or to a more fundamental shift in our understanding. The tension between Webb's observations and lambda CDM predictions is quantified through Bayesian model comparison and other statistical frameworks that assess how well different models fit the data and how much fine-tuning or ad hoc adjustment is required to achieve a fit. A model that requires extreme or implausible parameter values to match observations is disfavored compared to a model that fits naturally with moderate parameter values, even if both models can technically accommodate the data. The current situation, with some of Webb's most massive high-redshift galaxies appearing to require star formation efficiencies or timescales that are at or beyond the limits of plausibility within standard physics, has raised red flags and motivated the search for alternative explanations. Alternative explanations under active investigation include modifications to the stellar initial mass function, which could allow for more rapid buildup of stellar mass if stars form with a different distribution of masses in the early universe. A top-heavy initial mass function, with more massive stars than in the local universe, would produce more light per unit mass and would cycle gas through stellar evolution more rapidly, potentially speeding up chemical enrichment and subsequent generations of star formation. However, a very top-heavy function would also produce large amounts of ionizing radiation and metal-enriched supernova ejecta, which should have observable consequences for the surrounding gas and the cosmic reionization process. Checking whether these predicted consequences match observations provides a test of the top-heavy IMF hypothesis. Primordial magnetic fields, if present in the early universe, could affect the collapse of gas clouds and the fragmentation of those clouds into stars, potentially altering star formation efficiency. The origin of cosmic magnetic fields remains uncertain. They could be primordial, generated during the inflationary epoch or by phase transitions in the early universe, or they could be produced by astrophysical processes such as the Biermann battery mechanism in shock waves or by dynamos in the first stars and galaxies. Strong magnetic fields in the early universe could suppress fragmentation and lead to the formation of more massive stars, or could aid in angular momentum transport and allow gas to accrete more efficiently onto protogalactic disks. Observational evidence for primordial magnetic fields is limited, but their potential role in early structure formation is being explored theoretically. The equation of state of dark energy, the relationship between its pressure and energy density, determines how dark energy's influence changes over time. A cosmological constant has an equation of state parameter WW equal to -1, meaning its energy density remains constant as the universe expands. Dynamical dark energy models, such as quintessence, allow W to vary with time, potentially being different in the early universe than today. If W was less negative in the early universe, dark energy would have been less dominant, allowing matter to clump more efficiently and structure to form more rapidly. Observations of the distance redshift relation through supernovae and baryon acoustic oscillations constrain W as a function of redshift, but there is still some room for variation within observational uncertainties. Whether such variation could resolve the Webb tension without conflicting with other observations is a question being actively investigated. Early dark energy models postulate a contribution to the energy density in the early universe from a component that subsequently decays or becomes negligible, distinct from the late-time dark energy that drives the current acceleration. Such a component could affect the expansion rate at early times, altering the timeline of structure formation and potentially increasing the matter density available for collapse. Early dark energy could also affect the sound horizon at recombination, imprinting a signature on the cosmic microwave background that has been sought but not definitively detected. The viability of early dark energy as an explanation for both the Hubble tension and the Webb galaxy tension is under investigation, with mixed results so far. The neutrino sector of particle physics, while well studied in terrestrial experiments, still harbors uncertainties relevant to cosmology. The absolute masses of neutrinos are not yet known, only the mass differences between the three neutrino flavors. Cosmological observations constrain the sum of neutrino masses through their effect on structure formation. Neutrinos, being light and fast-moving, suppress the growth of structure on small scales. If neutrino masses are toward the higher end of the allowed range, this suppression could be significant enough to affect the formation of early galaxies. Alternatively, if there are additional sterile neutrino species that do not interact through the weak force, they could contribute to the dark matter or affect the expansion rate in ways that alter cosmological predictions. Sterile neutrinos have been invoked in various contexts to explain anomalies in neutrino experiments, but their existence remains unconfirmed. The reheating phase after inflation, when the energy stored in the inflaton field is converted into the hot plasma of particles that fills the early universe, is another area of uncertainty. The efficiency and dynamics of reheating depend on the coupling of the inflaton to other fields and on the details of particle interactions at very high energies. Different reheating scenarios can lead to different initial temperatures and particle abundances, potentially affecting the subsequent evolution of the universe, including nucleosynthesis, the formation of dark matter relics, and the growth of perturbations. While reheating is generally expected to be efficient and to establish the standard hot Big Bang initial conditions, variations are possible and could have observational consequences. The epoch of recombination, when electrons and protons combined to form neutral hydrogen and the universe became transparent, is well understood theoretically, and the predicted features match observations of the cosmic microwave background in exquisite detail. This agreement provides strong support for the standard cosmological framework at that epoch, around 380,000 years after the Big Bang. The subsequent dark ages, from recombination until the formation of the first stars, are less well understood observationally because there are few direct probes of this period. The formation of the first stars, ending the dark ages and beginning the cosmic dawn, marks a transition that Webb is now observing directly. Understanding this transition and the subsequent rapid assembly of galaxies is one of Webb's primary science goals. The first stars, forming from primordial gas without heavy elements, are predicted to be very massive, hot, and short-lived, with lifetimes of only a few million years. These population 3 stars would have produced copious ultraviolet radiation, ionizing surrounding gas and contributing to reionization, and they would have exploded as supernovae, enriching their environments with the first heavy elements. Detecting individual population 3 stars directly is beyond current capabilities because they are expected to be too faint and too rare, but their collective effects on the intergalactic medium and on the chemical composition of early galaxies should be observable. Webb's spectroscopic observations are searching for the signature of population 3 stars in the light of early galaxies, particularly the absence of metal lines that would indicate pristine gas. Finding such signatures would confirm a key prediction of the standard model of the first stars. The initial mass function of population 3 stars is uncertain because the conditions of their formation, extremely low metallicity, high-temperature cosmic background radiation, absence of dust, differ from those in the local universe where the IMF has been measured. Simulations of population 3 star formation suggest that the first stars could have masses of tens to hundreds of solar masses, much higher than the typical stellar mass in the local universe. Such massive stars would produce very different feedback effects and metal yields compared to a more normal IMF, and their presence would significantly affect the early evolution of galaxies. Constraining the population. 3IMF, through observations of early galaxies, is a major goal of current research. The contribution of black hole accretion to early galaxy energetics is another factor that could influence observed properties. If early galaxies contained rapidly growing black holes, the radiation from those black holes could contribute significantly to the total luminosity of the galaxy, potentially causing mass estimates based on luminosity to be overestimated if the black hole contribution is not properly accounted for. Distinguishing between stellar light and AGN emission in high redshift galaxies requires detailed spectroscopic analysis to look for characteristic emission lines and continuum shapes associated with black hole accretion. Webb's spectroscopic capabilities are enabling such analysis, revealing in some cases that a significant fraction of the light does come from AGN, which complicates the interpretation of stellar masses. The clustering of AGN in the early universe provides information about the masses of the dark matter halos that host them and about the mechanisms by which black holes and galaxies co-evolve. If high redshift quasars are found predominantly in the most massive dark matter halos, this would suggest that black hole growth is most efficient in the most extreme environments. If instead they are found in a broader range of halos, this would indicate that black hole growth can occur efficiently even in more typical galaxies. Webb's surveys are beginning to map the spatial distribution of high redshift quasars, providing the first robust measurements of their clustering properties and the first constraints on the halo masses of their hosts. The relation between black hole mass and galaxy properties, well established in the local universe, may differ at high redshifts if black holes grew more rapidly relative to their host galaxies in the early universe. Such a difference would have implications for models of galaxy formation and for the feedback processes that regulate both star formation and black hole growth. If Webb's observations reveal that the black hole to stellar mass ratio was systematically higher in the early universe, this would suggest that black holes formed earlier or grew faster than galaxies, and that the co-evolutionary relationship has changed over cosmic time. Understanding the origin and evolution of this relationship is a major unsolved problem in astrophysics. The gamma-ray bursts associated with the deaths of massive stars, being among the most luminous transient events in the universe, can be detected at very high redshifts and serve as probes of the early universe. The rate of long-duration gamma-ray bursts, which are associated with the collapse of massive stars, traces the formation rate of such stars and thus provides an independent measure of the high redshift star formation rate. Comparing the gamma-ray burst rate with the star formation rate inferred from galaxy surveys provides a consistency check on models. The afterglows of gamma-ray bursts, fading over hours to days, can be observed at multiple wavelengths and their spectra analyzed to determine the properties of the host galaxies and the intervening intergalactic medium. This technique has been used to study galaxies that would be too faint to detect directly, complementing the direct imaging and spectroscopy performed by Webb. Gravitational wave astronomy, still in its infancy with the detection of merging black holes and neutron stars by LIGO, Virgo, and CAGRA, will extend to cosmological distances with future space-based detectors such as LISA. Gravitational waves from mergers of supermassive black holes, expected to occur as galaxies merge, would provide a direct probe of black hole assembly and galaxy merger history at high redshifts. The rate of such mergers as a function of cosmic time is predicted by models of hierarchical structure formation and could be affected by the same uncertainties that plague models of galaxy formation. Detecting or placing limits on the gravitational wave background from supermassive black hole mergers will provide yet another constraint on cosmological models and structure formation scenarios. Multi-messenger astronomy, combining electromagnetic observations with gravitational waves and neutrinos, is opening new ways to study cosmic phenomena. Neutron-star mergers, which produce both gravitational waves and electromagnetic transients, including colonovae powered by radioactive decay of heavy elements synthesized in the merger, provide laboratories for studying nuclear physics under extreme conditions and for measuring the Hubble constant through the combination of gravitational wave distance measurements and electromagnetic redshift measurements. High-energy neutrinos from cosmic accelerators such as blazars and tidal disruption events carry information about particle acceleration mechanisms and could in principle come from very high redshifts, providing another window into the distant universe. The cosmic infrared background, the diffuse glow of infrared light that fills the sky, contains contributions from all the stars that have ever formed, integrated over cosmic history. Measurements of this background and its fluctuations provide constraints on the total amount of star formation and its distribution across time and space. If there was significantly more star formation in the early universe than the Standard Model predicts, this should show up as an excess in the cosmic infrared background. Current measurements of the infrared background are broadly consistent with models based on pre-Webb galaxy surveys, but new measurements incorporating Webb's findings will provide updated constraints that may reveal tensions. The connection between cosmology and fundamental physics extends beyond dark matter and dark energy to include questions about the dimensionality of spacetime, the unification of forces, and the ultimate structure of matter and energy. String theory, for example, predicts that spacetime has more than the 3 spatial dimensions and 1 time dimension that we observe, with the extra dimensions being compactified to sizes so small that they are not directly detectable. The geometry and topology of these extra dimensions determine the effective low-energy physics, including the masses of particles, the strengths of forces, and the values of cosmological parameters. While string theory has not yet made specific testable predictions for cosmology, it provides a framework within which questions about initial conditions, fine-tuning, and the cosmological constant might eventually find answers. Loop quantum cosmology, an application of loop quantum gravity to cosmological settings, predicts that the Big Bang singularity is replaced by a quantum bounce, where the universe contracts from a previous phase, reaches a minimum volume at which quantum gravity effects halt the collapse, and then expands into the current phase. If this picture is correct, the initial conditions of our observable universe are determined by the final conditions of the previous contracting phase, potentially explaining the smoothness and flatness of the universe without invoking inflation. Loop quantum cosmology makes predictions for observational signatures that might distinguish it from standard inflationary cosmology, including specific modifications to the primordial power spectrum, but these signatures have not yet been detected. The ekpyrotic and cyclic models of the universe propose that the Big Bang was not the beginning of time, but a transition in a cyclic history where the universe undergoes repeated cycles of expansion and contraction, with each bang corresponding to a collision between branes in higher dimensional space. These models offer alternatives to inflation for explaining the initial conditions and have their own predictions for observational signatures, including a blue-tilted spectrum of gravitational waves. Observations of the cosmic microwave background have not found evidence for these signatures, placing constraints on ekpyrotic and cyclic models, but they have not been definitively ruled out. The holographic principle, inspired by black hole thermodynamics and developed within string theory, posits that the information content of a region of space is proportional to the area of its boundary rather than its volume, suggesting that our three-dimensional universe might be a holographic projection of a theory defined on a lower dimensional boundary. The ADS/CFT correspondence, a specific realization of the holographic principle, relates gravitational physics in anti-de Sitter space to a conformal field theory on the boundary. While ADS/CFT applies to a space-time geometry different from that of our universe, it has inspired speculation about holographic descriptions of cosmology and quantum gravity more generally. Whether such ideas can be extended to realistic cosmological settings, and whether they make testable predictions remain open questions. Quantum cosmology, the application of quantum mechanics to the universe as a whole, faces profound conceptual challenges because it requires treating the entire universe as a quantum system, raising questions about the meaning of the wave function of the universe, the role of observers, and the interpretation of probabilities in a context where there is only one universe. The Wheeler-DeWitt equation, a proposed quantum equation for the wave function of the universe, is difficult to solve and interpret, and different approaches to quantizing gravity lead to different versions of quantum cosmology. Despite these challenges, quantum cosmology offers a framework for addressing questions about the origin of the universe and the initial conditions, potentially explaining why the universe began in a low-entropy state without invoking external causes. The arrow of time, the fact that physical processes exhibit a preferred direction in time from past to future, is intimately connected to cosmology through the second law of thermodynamics, which states that entropy increases over time. The low-entropy initial state of the universe, evident in its smoothness and uniformity at early times, is a boundary condition that has not been explained by fundamental theory and may be related to the quantum state of the universe at the Big Bang. Understanding why the universe began in such a special state and how this connects to the arrow of time is one of the deepest questions in physics, touching on issues of causality, determinism, and the nature of time itself. Generate the complete documentary now.